Hello, everyone. In this session, we're going to talk about transformers. These are what we're going to talk about. First of all, as a recap, we are going to talk about applications of sequence-to-sequence models. And one of them is image captioning. And after that, we're going to have a look at transformers. In fact, sequence-to-sequence plus attention is what we saw in the last session. And generalizing attention mechanism leads to transformer architectures. And after that, we will discuss pre-training mechanisms for transformers. Nowadays, we all know ChatGPT and other transformer architectures. And I'm going to share some of the pre-training schemes for transformers. First of all, the applications of sequence-to-sequence models. How can we design an architecture for image captioning? The task of image captioning receives an image and it outputs the description of the image. And the output, the description, can be represented as a sequence of words. And first of all, what we need to do is we need to extract spatial features from a pre-trained CNN. And, CNN contains two parts. The first part is backbone for feature extraction, plus a series of FC layers, and then softmax. And this calculates scores for each class. However, here, what CNN means is this backbone. It does not include these fully connected layers or softmax layers. Anyway, let's say the original image size was H0 times W0 times 3. Generally, images are in 3 channels, RGB, and after passing through the CNN backbone, it becomes H times W times D. And this H is smaller than H0, and this W is smaller than W0. Then what we do is we pass an MLP that aggregates the information in this feature map. And that becomes the first or initial hidden state of the decoder. And the difference between the ordinary sequence-to-sequence model we saw in the last session and this image captioning architecture is that the encoder entails CNN rather than an RNN. That is the difference. After that, everything else is pretty much the same. So we pass this initial hidden state, and then we calculate the next hidden state. So receiving the previous hidden state, previous output, and context vector. And then we generate an output for the current time step t. And we repeat this process again and again, as we did in the sequence-to-sequence models. So once again, the difference between the sequence-to-sequence models for machine translation and the sequence-to-sequence model, this is not actually sequence-to-sequence model, but this is an architecture for image captioning. Is that here, we are using 2 RNNs. So for encoder, we use RNN. For decoder, we use another RNN. However, for image captioning, we use CNN for encoder and use RNN for decoder. So the latter parts are the same. However, the encoder architecture is somewhat different. And here, the same problem occurs as we encountered in the case of ordinary sequence to sequence. In that case, the input sequence or the information of the input is bottlenecked through this context vector C. And model needs to encode everything or every information it wants to say within C. And this is a problem if we want to generate really long descriptions. Let's say 100 words, then this context might not be enough. And to solve this problem, we came up with the idea of attention. And we can apply the same idea here to solve this problem. And this could also address another issue that if the input image is too long, too large, then these sequences might become very long. In that case, this context vector might not be big enough to encode all the information inside this image. Therefore, introducing attention can solve these kind of problems. New context vector at every time step. And each context vector will attend to different image regions relevant at the current time step or the current time step. And we're going to do the same thing. However, the only difference is in the previous case, we applied 1D attention. And for the images, what we are going to do is 2D attention. That's the only difference. Everything else is the same. Therefore, what we are going to do is multiply this hidden state of the current time step with the feature maps. So Z00 times H0, Z0, 1 times H0. We repeat this process for all the feature maps, all the elements of the feature map. Okay, then we get the alignment score. And after that, we apply softmax function. Then this alignment scores becomes attention. And they sum up to 1, and they are between 0 and 1. Therefore, everything is just the same. The mechanism is just the same. However, we're applying the attention mechanism to 2D arrays rather than 1D array. And we give this attention score and multiply these attention scores with this feature map in an element-wise way. Then we use this one as a context vector. And to use this as context vector, we multiply this attention score with this element, this one with this one, and then sum them up. Then we can come up with just one context vector having the same dimension as the hidden state. They might have different hidden states. However, we'll discuss how we can change the dimensions, but let's say the dimensions are the same here. Then we calculate new context vector for at every time step, like this. And each time step of decoder uses a different context vector that looks at different parts of the input image. When it tries to generate the word person, it might have bigger attentions around this area. And when it tries to generate the word hat, then this model might have big attention around this hat region. Okay, this entire process is differentiable. And we don't have to supervise or give supervision signal in regards to how to learn these attention weights. This is all automatic. This is one example. Soft attention looks like this. When it describes, the decoder describes bird, as you can see here, attention is mostly on the bird. Okay, and when you think about over, it gives a little more attention to the sea or the water. And here you can see hard attention. Hard attention is either 0 or 1, and this is not differentiable. Therefore, you need to learn this hard attention through reinforcement learning. And as you can see here, hard attention is not necessarily superior to soft attention. And as you can see here, when the decoder tries to describe frisbee, the attention is on the frisbee region. And when it describes a dog, the attention is on the dog area like this. And as you can see here, it's amazing that the model automatically learns where to attend. Okay, this is the summary. When we do image captioning with RNN and CNN, we can apply the same attention mechanism that we applied for machine translation. And even though we extended 1D attention to 2D attention, it perfectly works. Even though we don't give any supervision in regards to attention, it works perfectly well. All right, from now on, let's talk about transformers. Attention we just saw in image captioning looks like this. The input was features, and this was 2D with depth of D. And we had another input, which was query, and it has the shape of D. And what we did was perform element-wise multiplication or dot product. Here, whatever you want to choose is okay. So you can choose dot product or MLP. Anything is okay. After that, we calculated the alignment, and we turned this alignment into scores by utilizing the softmax layer. And this alignment becomes attention after passing through softmax layer. And this attention sums up to 1. And they are between 0 and 1 because this is one kind of probability distribution. And after that, what we did was perform element-wise multiplication between this attention score map and this feature map, and then sum them up. Then we can get the context vector. And we saw in the last session that we need to perform summation in certain directions. Therefore, you need to be very careful where you are taking the sum, along which axis, okay? And this context vector has the same dimension as this query. And this query has the same depth as the feature maps. And I mentioned this in the last session that the attention mechanism or the attention operation does not care about the order of the features. And this property is called permutation invariant. This attention operation doesn't care about the ordering of the features. And you can generalize this attention mechanism by stretching the 2D mechanism, 2D maps, into n vectors. Okay, so from now, we are going to talk about just 1D cases because generalizing 2D or 3D cases is quite simple because we can just stretch those 2D and 3D vectors or arrays or tensors into 1D vectors. So we first calculate the alignment using this equation. And then we calculate attention and generate the context vector following this equation. And here, we're going to change this function to a simple dot product. It doesn't really matter because there are other following operations. Even though we are using just simple dot product, it is enough, powerful enough to express all the attention mechanism we want to express. Okay, and this only works well with key and value transformation trick. And I'm going to introduce this in the following slides. So don't worry. And another thing we're going to introduce is this division by square root of d. D is the dimension of this query or the input vectors. Why do we need to do this? Because larger dimensions means more terms in the dot product sum. So the variance of the logits becomes higher. And we don't want that to happen. We want stable performance regardless of the vector dimensions. However, if the vector dimension is small and its performance is okay, and if the vector dimension is high, the performance becomes unstable, that's not what we want. And by normalizing these values using this square root of d, then we can reduce the effect of large magnitude of vectors. Okay, that's why we are using scaled simple dot product. We're not just using simple dot product, however, scaled simple dot product. Okay, and another generalization we're going to introduce here is we're going to use multiple query vectors. This is not mandatory. However, we can use multiple queries like this. And this means each query creates a new output context vector. Therefore, if we have 3 queries, then we're going to end up with 3 context vectors. And notice that the input vectors are used for both the alignments as well as the attention calculations. Here, we're using these input vectors to calculate alignments and to calculate these context vectors after multiplied with attention. However, we can sometimes use different values when we want to calculate context vectors. Or we might want to use different values for calculating alignments as well. To address this issue, what we are going to do is change input vectors into keys using some type of MLP here, like this. So we are not just using the input vectors, but turn these input vectors into keys. And we are going to turn these input vectors into values using another MLP here to values. Okay. Then when calculating alignments, we're going to use keys. And when calculating context vectors, we're going to use values. And by using key, query, and values, we can improve the representative power of this attention mechanism. And if we don't apply key and values like this, then this simple dot product will not work. We need to apply MLP here, okay? And recall that the query vector was a function of the input vectors here, okay? So what it means is we can use input vectors as queries. In that case, we say this is a self-attention. In the previous case, it was general attention layer. However, if the queries are also from the input vectors, then we say this is self-attention. So the query vectors are now calculated from this input, and we are applying another MLP here. Okay, and no input query vectors anymore. And another thing I need to mention here is queries might have different dimensions than the context vectors like this. In the previous case, the query vectors and the context vectors had the same dimension. However, in the generalized attention mechanism, they don't have to have the same dimension. Even though they can have, you can choose. However, in the previous case, there is no options. They should have the same dimension. This is another generalization. Okay, then everything else is pretty much the same. We turn these input vectors into queries, keys, and values, and get context vectors like this, okay? So the self-attention layer attends over sets of inputs. We don't have to feed any other things, but only the input. And self-attention is permutation equivalent, and it doesn't care about the orders of the inputs. So here in this case, even though the input is 1, 0, 1, 2, the output becomes 0, 1, 2. And if you change the order, like 2, 1, 0, then the outputs also changes the order, 2, 1, 0. However, this Y2 is the same as this Y2. And this Y1 is same as this Y1, and this Y0 is same as this Y0. So permutation equivariant means even though we change the order, the outputs as a set is the same. However, if you change the order of the input, the output also changes the order following the input's order. And this could be a problem because sometimes the languages or spatially ordered image features have orders. If you change the order of words, sometimes the meanings change. Therefore, permutation equivariant is not always desirable. And how can you address this? We can address this problem by introducing positional encoding. What is positional encoding? We concatenate or add special positional encoding to each input vector. Then, if you change the order of the input, then this position encoding differentiated, then they are not permutation equivalent anymore. And the properties that position encoding should entail are following. First of all, it should output a unique encoding for each time step. There should be no overlapping encodings. And distance between any two time steps should be consistent across sentences with different lengths. This is also very important. And here, these two things are talking about consistency. And the third property is our model should generalize to longer sentences without any effort. Its values should be bounded. This is also very important. And the fourth one is it must be deterministic. This is, of course, natural property of position encoding. If the values or encoding changes over time, then it is meaningless. Okay? And there are two options for position encoding. The first one is learn a lookup table. Learn a set of parameters to use for position encoding. And then lookup table contains T times D parameters. And the second option is design a fixed function with these requirements. And we generally use sine and cosine functions. as you can see here. Okay, so up to this point, we talked about general attention mechanism and self-attention mechanism. Here, we're going to talk about masked self-attention layer. What does it mean? When we want to learn language models, we want to input at once and get outputs at once. This is only possible for training stage. In the inference stage, we don't have future inputs, so we need to sample, like get one input, and then get one output, and put this as the next input, like this, and then get another output, and put this as the next input, like this. This is what we need to do for training language models. So this is for training, and this is for inference. In the stage of inference, we can't access to the future inputs. However, in the case of training stage, we can get the future inputs as well. And this is called teacher forcing. However, if you just naively apply this teacher forcing scheme for training transformer-based language model, then it will require, or it will just attend to the future time steps. And we need to prevent this phenomenon. So we need to prevent vectors from looking at future vectors. How? By manually set alignment scores to -infinity. In this case, query 0 should not attend to query 1 or 2, but it can attend to itself. Therefore, this value remains. However, we assign -infinity and -infinity to future time steps like this. And when you look at query 1, this can look at past input, which is query 0, and current input, query 1. However, it cannot look at the future time step, query 2. So this one is assigned as -infinity. This is called masking. Here, by setting -infinity, these values become 0, 0, 0. So they get no attention. Okay? And another type of extension is multi-head self-attention layer. Rather than calculating just one context vector at a time, I mean, one set of context vectors, we can run multiple heads in parallel. And after that, we concatenate those context vectors. Why do we need to do this? Because you remember one-to-many or many-to-one alignment or many-to-many in the case of machine translation. Therefore, sometimes these models require more than one context vector at a time, because one word can correspond to multiple words and vice versa. Therefore, employing multi-head self-attention can improve the performance. All right, so the difference between general attention and self-attention is like this. Self-attention input becomes both key, query, and value. However, in the case of general attention, we have different sets of keys, values, and queries. Okay, and let's have a look at a CNN with self-attention. In this case, why do we need self-attention? Because if we divide this part and look at this lower part, we might not know whether this is from a tiger or a cat. However, if we attend to this region, then we can certainly recognize this part is from a cat rather than a tiger. Like this, if we attend to other regions of the input image, then we can get more information about the region. And we can better learn good features. That's why we need self-attention. And these features becomes both queries, keys, and values. Then, using keys and queries, we calculate attention weights like this. We need to pass through the softmax layer. And then multiply these attention weights with these values and do sum. Then we can get context vector like this. Okay, this should be W. And we can make a residual connection path like this. And this becomes a self-attention module. Okay, let's compare RNNs to transformers. The advantage of RNNs are like this. LSTMs work reasonably well for long sequences. However, transformers are good at long sequences, so much better. And each attention calculation looks at all inputs. However, RNNs expect unordered sequences of inputs. And transformers can handle both unordered sets or ordered sets. And in the case of RNNs, we need to calculate in a sequential order. For calculating y, let's say 5, we need to calculate y 1, 2, 3, 4, 5. This should be sequential. Without calculating y4, we cannot calculate y5. However, in the case of transformer, parallel computation is possible. In the case of training, in the case of inference, we need to be sequential. However, that is not a big problem because we don't usually do inference in parallel. It's okay. And the bad news about transformer is it requires a lot of memory. This alignment and attention scalars need to be calculated and stored for a single attention head. Okay, nowadays GPUs are getting bigger and better, but still it requires a lot of memory and computation. Okay, up to this point, we've discussed different ways of configuring general attention, self-attention, and masked attention. And let's use these building blocks to build our transformer architecture. Transformer encoder block is made up of n encoder blocks. We can stack more encoder blocks, and using more encoder blocks means more representative power. And let's dive into one encoder block. First, we add positional encoding. Then attention attends over all the vectors. Multi-head self-attention follows. Then there is a residual connection. And then a layer norm follows. And this layer norm is applied over each vector individually. Then MLP, another residual connection, and layer norm again. And this is one encoder block. The input is set of vectors and the output is set of vectors. Because we give only vectors, it is self-attention. And what about decoder blocks? So we stack n transformer encoders and get context vectors at the last layer, okay? And the decoder block is also made up of n decoder blocks. And this decoder blocks receives the context vectors from the encoders, okay? So this encoder block produces a set of context vectors like this. And this decoder blocks use these context vectors from the encoder. And everything else is pretty much the same. However, we need to use masked multi-head self-attention. So here multi-head self-attention is now masked multi-head self-attention because we don't have access to future parameters. Then here, rather than having self-attention, so this was originally just layer norm. However, decoder has another attention, multi-head attention. This one, key and values, uses this context vector from the encoder. And this one is just multi-head attention. Then these parts are just the same. Okay, so transformer decoder block receives a set of vectors and a set of context vectors. And in the outputs, a set of vectors. And masked self-attention only interacts with past inputs. And multi-head attention block is not self-attention. No self here, okay? No self. It receives context from the encoder. These architectures, the encoder block and encoder blocks, are highly scalable and highly parallelizable. However, they require high memory usage. And we can perform image captioning using transformers. So rather than just using RNN, we can stretch these 2D feature maps into 1D feature maps like this, and give these inputs to transformer encoder, and this will create context vectors. And we start generating new sentences. However, in the training stage, we can use teacher forcing, and this goes in parallel. And we can use mask self-attention here, and then train these sentences. And therefore, there is no recurrence at all. These are all parallelizable. And perhaps we don't need convolutions at all. We can just use transformers for handling the original pixel values like this. And these architectures are called vision transformers. Transformers came out 2017, and vision transformers came out in 2020. And around this time, during this time, transformers were majorly used for NLP or speech recognition, like sequential data. However, after vision transformer, researchers started to use transformers for processing images. And these three vision transformers are very big. However, their performance is also very good. Even it is compared to ResNet, it outperforms ResNet. And nowadays, everyone uses vision transformers for object detection, image classification, like all kind of vision tasks. Okay, so these are some graphs. Transformers are better. Okay, people are using transformers for ImageNet task or object detection.